Yes, I'm going to be talking about context switching in PowerPC Linux. Thanks very much for not going to Rusty's talk. So what we're going to be talking about today, we're going to start off with a quick overview of what PowerPC is, and then a little bit of an overview of the architecture, mostly relating to context switching. Then talk about what we do with context switching currently in Linux on PowerPC, what we've done to change it, the new version, and then some of the results and some to-dos of what we could do in the future. So, PowerPC, what is it? So these are the nice big fat machines that IBM make that I get to work on. In the middle there is the, as IBM affectionately calls it, the 795, which is a very large 1024 thread machine with up to 8 terabytes of memory. Very nice machine to play on. You can partition this up to lots of little machines, or you can have one great big Linux instance running on 1024 threads. We also go down to very small machines. You can have a little 4-core blade if you want, and these are all 64-bit PowerPC machines. Another PowerPC machine is the Blue Gene range of supercomputers. These guys have dominated the top 500 supercomputer list for the last few years. They're not on top at the moment, but they have done very well in the last few years. These are based on 32-bit PowerPC machines, or PowerPC cores. PowerPC is also used in embedded. The TiVo uses a PowerPC. And obviously we completely own the games market. So the PlayStation has a Cell processor, which is a 64-bit PowerPC processor, 2 threads with 8 vector processing units attached to it, closely coupled to the CPU. The Xbox 360 is a 64-bit PowerPC, 3-core. And the Wii is also a 32-bit PowerPC box. Of course, the big pink elephant in the room is these guys, which is not coming up. The big pink elephant is hiding, apparently.
You're holding it wrong.
I apologise, there we go. There's the big pink elephant, finally made. So Apple was running PowerPC, but obviously they're not now. So PowerPC Architecture, just going to give you a quick overview of what it means in relation to context switching. PowerPC is very simple RISC architecture. We have 32 64-bit general purpose registers. These GPRs are used on almost every instruction by every task in the system. And they're always context switched in and out. We also have a bunch of extended state. So we have some floating point registers. We have 32 64-bit registers. So that's about 256 bytes worth of data. A couple of cache lines in PowerPC. We also have some vector registers, Altivec registers. There's another 32, but these are 128 bits wide. And these are similar to MMX or SSE on you'd get in an Intel processor. And on Power 7, we added the vector scalar registers, the VSX registers, which is 64 128-bit registers. So we're talking here about another 1,024 bytes worth of extended state that would need to be context switched for every task. It actually turns out the VSX overlaps with the floating point and Altivec registers, so there's not additional state on top of FP and Altivec, it overlaps. We also have miscellaneous control and status registers to say if you divide two floating point numbers, whether the result is a 0 or not a number or infinity or whatever. And we also have, from an operating systems perspective, we can turn off these individual parts of the CPU. So you can say, turn off floating point. So if a user space program tries to run floating point instructions, it will trap into the kernel, and the kernel can decide what it wants to do, whether it can restore, whether it can let that user space program run that or not. And we have that for FP, Altivec, and for VSX. And these are quite important, which I'll talk about soon. So, context switching. What do we currently do? So just a quick little computer science operating system 101, what am I talking about slide. If you're running two tasks on a system, Linux will switch between them. If you've got task A and task B, we'll switch between them many times a second to make it look like they're both running at exactly the same time. And that's context switching. In reality, it looks a little bit more like this, where we have A running, it ends its time slice, then the kernel preempts A at the end of its time slice and goes, I'll save away its state into memory. Then it calls into the scheduler. The scheduler says, I want to run task B. So it goes, gets task B state from memory, pulls that into the CPU, and then starts task B. Task B then runs for its time slice, and kernel preempts it, and we wash, rinse, repeat over onto A and then B. So at the moment, we do lazy floating point restore. Now, I'm going to talk about floating point for the most of the rest of this talk. I will, at the end, talk about Altivec and VSX and how that differs. But for the majority of the talk, I'm going to be talking about floating point. So for floating point, we always save. At the end of a time slice, we always save. We always save the floating point state. But we restore on demand. So what does that mean? Well, the kernel decides it wants to run A, and A starts with the floating point unit off. And A, in this diagram, we have A as a floating point intensive task and B as a non-floating point intensive task. So A runs along with the floating point unit off. Then it wants to run a floating point instruction. But because the floating point unit is off, it traps into the kernel, and the kernel goes, okay, you want to run floating point. I'll restore your state from memory into the floating point unit, and then turn the floating point unit on and continue on. And then A can continue on rerunning that instruction until it ends its time slice. Then at the end of the time slice, the kernel goes, I better save away that state. It knows that A used the floating point unit, so it saves away that state always. And then, again, calls into the scheduler decides it wants to run B, and we restore B. But here we restore B with the floating point unit off. And this is great. This means that with this mechanism, if A and B are not floating point tasks, then we never have to actually save and restore the floating point, the floating point state. And it's on a per time slice basis. Just extending that a little bit longer, you can see that we have the original A and then B, and then A runs again. We have to then go and trap again. So every time that A starts its time slice, we have to trap into the kernel to restore our state. This just elaborates that a little bit more. We've split this out into the CPU task at the top and the floating point unit task at the bottom. Oh, sorry, it's dropped off the edge of the screen there. That's floating point unit task on the left-hand side there. Shows up okay here, so sorry about that. So CPU task at the top, floating point task at the bottom. You can see that the floating point task initially the floating point isn't really associated with anything. And then when A runs that first floating point instruction, the floating point unit gets restored with A's state. Then when B runs, before B runs, that floating point state gets flushed out to memory, so the floating point unit again has no state associated with it. So you can see while B is running, there's no floating point state up until A traps again on its second time. So currently, there's three possible places where our state could be. If our task is for a particular task, if a task is not running, we always save away its state at the end of its time slice, so it's always in memory. If it is running, the floating point state can be in the floating point unit if we have used floating point in this time slice, or it could still be lazily out in memory. And I'm going to expand on this as we go as it gets more complicated, as it gets more complex. So what do we do that's new? So we were restoring on demand and we've kept that, but what we're going to do is save on demand as well, rather than saving at the end of the time slice. and we're going to try and reuse the floating point state if possible. So what does this mean? So again, we have A and B. A is floating point intensive and B is non-floating point intensive. You can see A is running at the start with the floating point unit off. The floating point unit owns the A task, or is associated with the A task. Then the kernel starts task B, and it knows that, well, it's not going to use the floating point unit, so it comes with the floating point unit off, doesn't change the floating point unit task. You can see my FPU now, that's great. And it doesn't change the FPU task, so when A starts running again, it knows that the floating point state is already there, and it can just start A with the floating point unit on and not have to bother restoring that state, restoring that 256 bytes. So this is great. If C comes along and C is a floating point intensive task, we still need to go and save and restore, obviously. So you can see here, C comes in with the floating point unit off. The floating point unit is associated with task A. Then when C traps into the kernel, the floating point unit changes over to C. As the kernel saves and restores, saves A, it restores C. And then C can run with the floating point unit off. So we still have to take this trap if we're running two floating point intensive tasks. Going back to the possible places where our state could be now, if a task is not running, we now have an extra state where the floating point state could possibly be still in a floating point unit somewhere. It may have been lazily saved away. It could also be in memory, and again, if it was running, it could be in the floating point unit or in memory. But that's the same as before. So this is all very simple. This is great. Hopefully, we've saved some time. But we're missing a big piece here. The big piece is SMP, multiprocessor. What happens if we start migrating tasks from one CPU to another? What do we mean by this? So now we have CPU 0, or PU 0 apparently, PU 0 at the top and CPU 1 at the bottom, not floating point unit at the bottom. CPU 0 starts off running task A and then switches to some other task, doesn't matter what it is. Then CPU 1 comes along running another task, and it wants to switch over to A. But possibly we have our floating point state still on CPU 0. So we've now put the floating point units back in again. We've got CPU 0 and floating point unit 0 at the top, and CPU 1 and floating point unit 1 at the bottom. So somehow CPU 1 has to get its state from CPU 1. CPU 1 has to get it from CPU 0. Just going back to where our FPU or our floating point state could be for a particular task, the top is the same if we're not running. It's either in an FPU or in memory. If we are running, we have an additional state. It could be on our current FPU if we've used floating point in this time slice, or it could be on somebody else's floating point unit. It could be on a different CPU's floating point unit. So we've now got 5 possible places where our floating point state could be. So how do we do this CPU migration? So CPU 1 at the bottom decides it wants to run A. It goes and IPIs over to CPU 1 or inter-processor interrupt and says to CPU 1, please go and dump that state that you have. So whatever task is running on CPU 0 stops, gets preempted, and the kernel goes and takes the state that it has in the floating point unit and dumps it out to memory. It then communicates back to CPU 1 to say, that's all done, you can start A up now. So that's great. The problem here is the kernel on CPU 1 is just sitting around waiting for CPU 0 to do this. And this could possibly take a long time, and it's just kernel overhead. We really prefer not to do that. This is kind of the slow case CPU migration, but let's try and make it faster. So what we decided to do was start the IPI early, but then only wait for the results to come back when we need to. And essentially we're reusing our lazy restore here. So this is the same again. CPU 1 goes and IPIs CPU 0, but instead of waiting in the kernel, it now just starts task A straight away. but it starts it with the floating point unit off because it knows that it doesn't have the state there yet. CPU 1 goes and dumps the state, as we saw in the last, or a couple of slides back, then returns back to CPU 1 with to tell it that the state is there. And fortunately, in this case, it does it before A runs its first floating point instruction. Then A does run its first floating point instruction, it traps, the kernel goes, cool, my state's in memory, ready to go, it's not on somebody else's CPU, I'll just restore A, and away we go. With the floating point unit on. So this is the fast case. This is good. But CPU 0 could take a long time. So this is exactly the same diagram as the last one, except we've just changed the timing slightly. So here, CPU 1, IPI CPU 0, but CPU 0 takes a long time for whatever reason. It could be running with interrupts off and it doesn't receive the IPI for a while. It could have been sleeping, whatever. So it takes a long time to dump that state out. And task A runs a floating point instruction very early. So it actually runs it before the state is returned. So we now have to actually wait in the kernel. Now traditionally these traps, these floating point traps, have been taken in a hand-coded assembler and they're taken with interrupts off. Now waiting, as we're waiting here, with interrupts off is generally a very bad thing to do in the kernel. It's a nice recipe for deadlocks if you don't have any timeouts. So what do? We firstly check in the kernel to see if the state is there with interrupts off. If it's there, great, it came back in time, we can just restore A into the floating point unit. If it's not there, we have to turn interrupts on. So we turn interrupts on and we sit there and wait for the state to arrive. When it does arrive, when it eventually arrives, we turn interrupts back off again and we check to make sure that we didn't pick up somebody else's state. We may have been preempted off to somewhere else and may have potentially picked up somebody else's floating point state. So we need to dump that before we restore A back. So how do we implement this? We've got two new pointers. The first pointer is a per CPU pointer. If you want to use the floating point unit associated with this CPU, you need to be able to dump out the state in this current CPU. So this pointer will tell you whose state you currently own so that you can dump it. We've also created a per task pointer. If you want to context switch in a task, you need to know where to get it from, which CPU is it on. So this will tell you which CPU your state is on, or if it's in memory. I promised I'd mention Altivec. Altivec is exactly the same. Wash, rinse, repeat. The control logic around it is identical. The actual save and restore instructions are different because they're different registers. But other than that, it's all pretty much the same. VSX. I said VSX actually overlaps with the floating point and Altivec state. In actual fact, there's no additional state that VSX provides over Altivec. We've got a question up here.
Thanks. Maybe you'll get to this, but can you actually prove that this is more efficient than just saving the state when you're doing SMP and extra things like the FPU and Altivec are in use?
Well, I'm going to talk about some results later on, so maybe I'll answer that then.
It better be worth it.
So we also have the additional case that if we know that FP and Altivec can be reused, in that nice case where we have A is a VSX intensive task and B is not, we know that if FPU and Altivec can both be reused, then VSX can be reused as well, and we don't need to save and restore that. A few other issues. We have a merged 32 and 64-bit kernel. I mentioned that these traps, these floating point traps, are all hand-coded assembler, so actually getting them to work with 32 and 64-bit with different MMUs and these run with the MMU on and off. Making sure that all worked was somewhat not trivial, and thank you, Ben, for helping. Power save, there's a couple of issues here. One is if you're going to go into power save, you want to get rid of any possible state that you have so that you don't get woken up later on to have to go and dump that. So that's one reason why before you go into power save, you want to flush your state that you have. The second reason is on bare metal systems, you may power down this package completely or power down the core and the state may be corrupted. So you really need to dump it in that case. Hot plug CPU, very similar to power save. You need to make sure that if the CPU is going to leave the system, that you've dumped the state already. Otherwise, it's not going to be accessible anymore. Different config options. This was a fairly minor issue. There's about 6 or 7 patches in this series, but making sure that they all compiled with, especially in 32-bit land where they actually care about having these different options off, SMP, FPU, Altivec, VSX, making sure that the entire patch series was bisectable with all these different configs options, whereas, again, non-trivial. Signals and ptrace, because we've now got these additional places where our state can be, if someone's ptracing you and wants to know your FPU state, you need to make sure that that's dumped out to memory. Ptrace and signals will read it from memory. They won't directly go and read it from the floating point unit. So you need to make sure that they're dumped out before you actually go and read it. The same when you're generating a signal context for a process. You need to make sure it's dumped. So to hopefully answer your question a little bit, this is the patch series. This is the complete patches, so it's actually not that invasive. If you look at it's mostly in PowerPC, and you look at the bottom line here, 635 insertions and 315 deletions. So we're only adding about 320 lines of code. And I did a quick little poll or had a quick look at the patches the other day, and about 150 lines of that is documentation. I probably removed a little documentation too, but it's not a horribly invasive. It's not a horribly invasive patch series. It does add some complexity, but we're pretty smart in PowerPC land, so. Or at least we think we are. So testing, what did I do to test this? I actually coded up the Altivec version first because Altivec isn't used nearly as much as floating point, and this was easier to get a system booting and running so I could run tests. Once Altivec was somewhat stable, I started looking at implementing the floating point version. And once I'd done that, just booting a distro kernel, because glibc, especially in 64-bit, will use VSX in its mem copy, you'll notice pretty quickly if you start corrupting state. So just booting a distro up to user space with all its daemons was a reasonable test at that point. Then I started looking at a custom floating point test. I don't care what the computation is at this point. I just care that I'm not corrupting the state in user space. It is, to kind of come back to what you were saying, it is reasonably complex, and if you screw up, the consequences are quite bad. You corrupt user space state, and that's a really, really bad thing to do. So with this test, I was trying to make sure that we're not corrupting state at all. So it's a very simple test here. The meaty bit's in the middle, A equals B equals some constant value, and then we just check to make sure that it's always the same. And we just sit there and spin on that, and if it ever pops out into that printf, then we know that we've corrupted our state. Couple of things to note, interesting things to note about this test. If you just have while A equals B without the B equals C, and A and B are non-volatile, GCC just compiles that out to a branch to self. If you make A or B non-volatile, it won't compile it out, but when you do the printf, A and B will be reloaded from memory, so you don't get the value that was actually corrupted. So having the combination that we've got up there, where C is a volatile and we reload, you still get to see the corrupted state, but you don't get GCC getting in your way. So some results. So I started off just writing a very simple benchmark. Again, I don't care about what the actual FP or floating point computation is. I just care that more time is allocated to user space rather than to the kernel overhead is reduced. So all I did was write a simple test that started at 0 and counted up to a maximum and see how long it takes. So if I do this, no performance improvement. But there was no regressions either, so that's good. But why is that? So we go back to our original diagram, which looked like this. And you see A, then a bit of kernel, then B, then a bit of kernel, then A. Unfortunately, it doesn't really look like this. It actually looks a lot more like this, which is A, and then a teensy little bit of kernel, and then B, and then a teensy bit of kernel. And in actual fact, if you run just two processes on PowerPC don't do any operating system calls, you end up only getting about 40 or 50 context switches per second. So the kernel really doesn't contribute much in this test. So I thought about how are we going to try and exaggerate this kernel aspect. So I started talking to Anton. Anton Blanchard has a little context switching micro benchmark you can find there. It seems to be loosely based on BW pipe in LMbench. And this is the core of the test. Create two pipes, we fork. One side goes off to one while loop, which does a read-write, and the other side goes off to a write-read, which looks like that. Task A, task B, A does a write, B reads it. Two closely coupled tasks. So hopefully, what was looking like that with these tiny little bits of kernel will look more like that, where you have these gigantic bits of kernel. When I do run this test, sorry, I forgot to mention that when we run this test, we bind it to the same CPU. So it's on the same CPU, so they don't end up on different CPUs. If we do this, we get about 40 to 50,000 context switches per second. So a lot more kernel overhead. So if we do this, what happens? No performance improvement. But no regressions again. But we've completely forgotten about floating point. So what happens if we stick a little bit of floating point inside A, and B we leave without any floating point? So we get this nice, hopefully get this nice state that we saw before where A just owns the floating point unit and we never have to actually context switch those 256 bytes. If we do that, what happens? We get a 4% improvement in context switching rates with floating point. With Altivec, we can get another 4%. And with VSX, we can get 8%. And it doesn't seem like much, but user space will get this for free. They don't have to do anything. And we're just reducing kernel overhead, which is always a good thing. Well, generally a good thing, sorry. If we put floating point in both sides, sorry, did you want to?
I'll wait till then.
Okay. If we put floating point in both sides, what happens? So in this case, we're still going to take the trap and we still have to save and restore. What happens? No performance improvements, but no regressions either. LMbench, I decided I would actually run an industry standard benchmark. LMbench does some operating system level, quite a few operating system level tests. No regressions with LMbench, no significant performance improvements either though. So I promised a bit of a to-do. Signals and ptrace, I'd like to do more testing in signals and ptrace. I haven't done a lot of testing in that area yet, and it has generally been a very bug-rich environment in PowerPC. More benchmarking, always do more benchmarking. Lazy allocation of space. This is actually some more coding we could do inside PowerPC. For VSX specifically, we have 1,024 bytes of data that's allocated for every task, even if it's not using VSX, it always gets statically allocated. So if you say have 1,000 tasks, 1,000 times 1,000 is 1 megabyte of kernel data, or kernel memory. So that's somewhat significant. Unfortunately, because glibc uses memcopy, or uses VSX in memcopy, probably going to be allocated for almost every task anyway, so this may not actually help at all in reality. The other one that might be of more use, and I think this might be somewhat what you were alluding to, we could just auto restore. So if we think that this task is going to use floating point, instead of doing it lazily, we could just do it as we do the context switch. This would we'd still have to actually do the copy of that 1024 bytes, or it's about 4 cache lines, but we would be able to avoid the trap. The trap shouldn't cost us too much on PowerPC, but it will cost us something. So this could potentially buy us something, but so it's on my to-do list. And that's it. So thanks very much. Yep. We got some time for questions?
We do.
Yeah, me again. So this kind of sounds like a solution looking for a problem. Like, what was your use case that made you say, oh, we need this? Or I mean, and I work with embedded, so for me it would be like, well, we can get a smaller kernel footprint or something in memory, which probably isn't the case, because I think you've added about 150 lines of complexity to your kernel port, which isn't always good. But what about power saving? So when you turn the FPU off or something, can you like power it down or something to save power? And in which case then maybe, you know, there is a case for just always saving the state out and always powering it down. And can you, another kind of question is, yeah, at what point does the use of FPU and extra state make it worthwhile interrupting the other processor to get it there when you've left it there in that case? I'm just curious if you're going to look at those things.
I think we've got three questions.
Yeah.
My motivation was probably somewhat disappointing. I coded up the VSX side, being part of the IBM team doing Power 7. I coded up the VSX side and started to get familiar with this code and thought this kind of seemed like a cool idea, so let's give it a go. Yes, sorry, Ben's just pointing out that we actually used, the thing I didn't mention here is the lazy save and restore we did actually do when we didn't have SMP enabled. And in actual fact, I think that made the code more complicated because there was a lot of if-defs in there. This actually cleaned up a lot of that part. Because the embedded guys actually care about this. They actually care about compiling with INUP. So my main motivation at the start was, this is kind of cool. One of the things I probably should have done is run that benchmark with the A and B, the closely coupled, and see where it was in perf. And it turns out to be, you know, about the 5th or 6th item is, you know, at about 4%. So probably should have done that first, but, you know, maybe I'm not as smart as us PowerPC guys think we are. Power saving, if we turn the FPU off, I guess there's a potential there. I'd have to talk to some of our hardware designers whether that is in reality. If you're talking in a multi-threaded core, you've got other threads, like at least on Power 7, we have 4 threads per core. You're just turning it off on one thread, so you'd have to somewhat coordinate with the other threads, or you'd hope that the other threads would turn off their floating point units as well, from an architectural perspective, because they're behind the scenes, they're actually sharing the same FPU. So I guess there is a potential that they could do some power saving there, but...
Yeah, got a little bit careful as well is on those processors the architectural state of the FPU is preserved when it's turned off. So we have something in the architecture for embedded. I don't know if we kept it or kicked it out. I don't remember. Paul might. We had some wording in there that said that some embedded processors were allowed to trash the FP state when the FP was turned off. I don't think that was ever implemented actually on Power. But yes, if that was coming back, especially for the embedded field, we would have to make that an optional thing at runtime.
But we could potentially turn off the ALUs inside the FP unit, but keep the register files, because that's what we really care about. And your last question has escaped me, sorry.
Me too, I think I was just... Well, I don't know, what were the use cases?
Like, who came to you and said, oh, we're noticing a lot of context kind of switch overhead and
we have had some customers who've been trying to optimize these loops a bit, so it has had some attention in the past, but so it was partly that as well. The glibc guys, I think Peter Bergner was talking about he's one of the glibc guys inside IBM that does PowerPC. He was also wanting to see some performance improvements, and we had a bit of a discussion on our external list about it. So there was some push other than just this seems like a cool thing to code up concept. I think Ben wants to. Ben is the PowerPC maintainer, by the way, so.
Keep in mind that without that, we actually have to save and restore on every context switch 1K of state, which can be quite significant latency considering the speed of the CPU versus the memory and the caches nowadays. So also by the time you context switch, your cache for that state has probably been pushed out, and so you're going to take cache misses.
With 1024, you've got 4 cache lines plus, you've got the FP miscellaneous state plus
Yes,
the VSX, so
yeah.
you've got probably 6 cache lines.
So does that mean that essentially on SMP you will always have that cost, even if your task is not migrating or is not being switching with another task? So it does the ability to. The main point is to be able to maintain the state over multiple context switch of the same task if no other task goes in between, and the corollary to that is. To be able to do that in SMP, you then need to bring the whole shebang with the interrupt and everything. But we don't necessarily care about the migration case because it's a rare case. We just want to enable the non-migration case. But we had to solve the SMP problem to be able to do that.
There was a talk here last year by some guys in IBM LTC in India who talked about optimizing the scheduler for trying to place tasks based on what resources were shared. And they were looking at caches, so you tried to get try and split apart cache-intensive or memory-intensive tasks, and I think you could possibly do a similar thing with this, where you could try and split apart FPU-intensive tasks or keep them on different CPUs, so that you could try to get more of this good case that we have.
Did you try benchmarking the ideal case where you've got a single task, FPU intensive, on a single CPU with affinity set? Like your ideal, hi, I want to run a floating point monster, but it's my machine, that's all I'm doing. Because if context switch save...
Well, that was what the first benchmark that I ran.
Didn't you have 4 processes, but you still had the context switch with another process in?
So the diagram and what I actually did was a little bit misaligned there. The test that I ran was actually a single processor, but I did run it with 1 and with 2. But again, there was no performance improvement there. But that's just because you don't get many context switches with one process.
So I'm curious. You said that glibc uses the VSX stuff for everything, so that means you don't.
Not everything. It uses it for memcopy.
Okay,
64-bit will use memcopy.
But that means every context switch will have to save state on VSX. Would there be a win? Like, have you done any testing to stop glibc doing that, or does it get more of a win by using that?
So this is just a per time slice issue. So if you're not calling memcopy, then glibc's memcopy in this time slice, then you won't use VSX. So it won't have to be swapped in. Yep. Kernel threads as well.
Because when we context switch out, we don't know what else is going to come in. We had to save the state regardless, even if what's coming behind is a kernel thread. And for example, with heavy network benchmark, you can have quite a lot of software QD coming in and stuff like that. And those don't actually have any FP state. And so that limits the impact that they have on the underlying floating point task as well.
Yeah, we hardly use floating point inside the kernel. I think David had a question.
Did you gather metrics on how often you managed to optimize out?
Did I gather metrics on how often this worked? In my ideal case, almost every time. It actually did work. That case back where I talked about the slow IPI, where we had to actually go and wait. We had to actually wait for the data to come back from CPU 0. That was actually quite rare, that we had to actually wait in CPU 1 for that data to come back, even on a heavily loaded system and bouncing it around. So I did actually forget to mention, with that architected state test, I ran a number of those in my testing, and I bounced them around the machines to make sure that it actually was doing what I hoped and wasn't corrupting as it was bouncing around. But it wasn't that often that that we hit these really slow cases. I think we actually, in the kernel, we send the IPI very early, and it takes us a while to actually get back to A, even with the floating point unit off. So there's actually quite a bit of time there for that IPI to go away. I guess it would depend also on what drivers you're running and when they've got IRQs off and stuff like that. So it would depend a little bit on what workload is, and if I maybe didn't hit that one, then that would be a problem. But the lazy case worked. If I had A and B, those tightly coupled, it hit it almost every time. I can see in perf context switching, and my little stats that had was pretty much 1-for-1 for the number of context switches, for the number of lazy context switches.
So if you were put on the spot and had to say why
It didn't give you a performance improvement. Why?
Why? Because you're talking about the 4%, the whole thing? Because I don't think in reality it's that much overhead compared to the rest of the kernel. I think the scheduler, looking at the perf outputs, there's a lot of other things. And I had to actually disable some things that the distros have, like auditing, and there was a couple of other things to even get that 4%. So we'll just keep that between you and me. So yeah, it's just not. It isn't actually a huge part. It's kind of cool, and yeah.
Questions? We do have time for another question or two. No. Could you all put your hands together for our speaker?